All right, this will be AP Chemistry Notes, pages, I believe, 21 and 22. We start off with a combo problem. So we have a combustion reaction here. It says how many liters of oxygen measured at this pressure and temperature are required to react with 1 gram of octane. Well, first thing, this here is octane. And for those that don't have much of a background in organic chemistry, of course, oct is 8, and it means 8 carbons. And if you put enough hydrogens on the carbons so that all the carbons have an octet, you end up with 18. And what you would do is you just line up all your carbons like this in a row, and then start sticking hydrogens off as needed until every carbon has 4 bonds, and you'll find that it ends up being C8H18. Now, I mentioned octane and gasoline. When you go to get gasoline for your car, you'll see that most gas stations have an octane rating. If I remember right now you'll see an 87 and usually an 89 and a 91. And it's called the octane rating because it is based on the molecule octane and its thermodynamic properties. And it turns out if your car only needs 87, there's no reason to get the higher ones. But if your car needs 91, like if you have a sports car and it has a high compression engine and it requires 91, make sure you get the 91. Do not go lower and save a little money on the gasoline because it is very bad for your engine. All right, to the problem. Well, anytime you're given grams, you're probably going to want to turn that to moles, which I've done here. And then what we're looking for is the amount of oxygen. So I did stoichiometry, 1 to 12.5, and that gives me my moles of O2. I now have moles, pressure, temperature. So that's PV equals nRT. I like to solve for the variable first. So I solved for the V algebraically. You plug everybody in. Make sure that you convert the pressure into atmospheres and the temperature into Kelvin, which I've done. I made a note here. What I've seen some students do is rather than doing the conversion and then putting it in, they just write the conversion, which is here, right in there. You can do that if you want. I usually don't just because it gets too messy. You can do the same thing when it comes to the temperature conversion as well. But like I said, I usually just do the conversion and plug it in. And you get an answer of 2.74 liters of oxygen would be needed to perfectly react with 1 gram of the octane. Something I did in this problem, and this is the first time I believe I've done it, is this little slash right here, that slash. That's a way of keeping extra digits in your numbers, but reminding yourself that they're not significant. So in this case here, we get 0.1094 and other digits. And this has 3, this has 3, that's perfect. So really my answer should have 3, but I've not finished the problem yet. And so when you get something like a 4 here, if you want to keep that, and it's a good idea to keep that, what you can do to make it clear to yourself is go ahead and write that extra digit, but put a slash through it like that. And that'll remind you that go ahead and keep it in your calculator, but you're not going to count it as significant. You'll see that I did the same thing here. And that's a technique that I'll be using from here on. Second problem is also a combo problem. And I think of this problem as having 3 steps. Calcium reacts with water to form hydrogen gas and calcium hydroxide. So, okay, write the reaction. Calcium, water, hydrogen, calcium hydroxide. Don't forget to do diatomic for that hydrogen right there. Of course, balance it. How many milliliters of water at that density are required to produce 7 liters of dry hydrogen gas? All right, now the dry right here means there's no water vapor to worry about. And based on what I talked about in my last lesson, often when you collect a gas, you do it over water. And there's some water vapor to worry about. But in this case, it's saying don't worry about the water vapor. If it did say that it was over water, we would have to deal with that additional step. So in this case, because we have a volume and a pressure and a temperature, we can go ahead and do PV equals nRT and solve for our moles. Now be careful. This is the volume of hydrogen and the pressure of hydrogen and the temperature of hydrogen. So be careful when you get your moles right here. Don't think, oh, that's the moles of calcium or the moles of some other chemical. That's the moles of hydrogen. And so it's important first that you realize that, and second that you label it here just so you don't get lost. Then we can do stoichiometry. We can go from moles of hydrogen to moles of water using the 1 to 2 in the balanced reaction we wrote, and then moles to grams, and that gives us 10.6 grams of water. And we're almost done, but the problem wanted, where is it? Right here, the milliliters of water. But since it's water, and the problem reminds us that water is 1 gram per 1 milliliter, it's the same thing, like that. Now this next problem brings up a couple of things. First thing, they gave the reaction. When 0.5 moles of methane is heated, 2 moles of oxygen, the above reaction proceeds to completion. So all that's doing is emphasizing, don't worry about equilibrium, which we have not really done yet. That means it just goes forwards, like combustion reactions usually do. Determine the partial pressure of all gases present after the reaction if the total pressure was measured at 1.26. Now, my first version here, which is right here, I just use logic. And that's fine, but I don't think it's the best way to do it. I actually think the best way to solve this and keep track of what's happening is by using an ice chart. Now, there's a good chance in first year chemistry, you were taught ice charts, and you were taught it in equilibrium. And when you did ice, you said initial, change, and E was equilibrium, meaning what is the amount of each chemical once it reaches equilibrium? Well, it turns out an ice chart can be used for more than just equilibrium problems. You can think of the E as standing for end. In other words, the end of the reaction. Because equilibrium is itself the end of the reaction. It's reached equilibrium and there's nothing else really significant to notice. So realize an ice chart like I have here is just an organizational tool, and it's useful anytime you have a reaction occurring. So a question that comes up a lot in class is, when should we use an ice chart and when should we not bother? It's any time you have a reaction occurring and the amounts of chemicals are changing, whether it be in moles or molarity or whatever the case is. So in this case, they gave us the initial CH4, the initial O2. They didn't mention CO2 and water, so you just assume those don't even exist yet. Now, based on this scenario, if you have half a mole of CH4 and 2 moles of O2, that means that CH4 is your limiting reactant. It'll run out first, which means the amount of CH4 that reacts is negative 0.5. Well, the amount that reacts is 0.5, but we write it as a negative 0.5. The O2 is excess, so let me label this a little better. This one is limiting. And the O2 is excess. So now in the change row, we look at the balanced reaction. If half a mole of CH4 reacts, the O2 must be double that. So double 0.5 is 1. That's the amount that reacts based on the limiting reactant CH4. The amount of CO2 that gets produced is going to be the same as CH4 because it's 1 to 1. So it goes up by 0.5. The amount of H2O that gets produced, you can look at it a couple different ways. The H2O here is going to be the same as O2, so 1, or it's going to be double the CO2, double 0.5 is 1, or it's going to be double the methane, double 0.5 is 1. So you can compare any chemical in a balanced reaction to any other chemical that you know how much it's changing, and it better work out. Then you do the math. 0.5 minus 0.5 is 0 here. 2 minus 1 is 1. Nothing plus 0.5 is, of course, 0.5, and nothing plus 0.1, no, not 0.1, 1 is 1. If you add up all of your amounts of moles of chemical, you end up getting a total moles of 2.50 moles. And that's going to be useful because I want to use this mole fraction concept. Now, I take these numbers, and you either do it the logic way I mentioned earlier or the ice chart, which I think is better, to calculate the partial pressure of each of these chemicals, and they're all gases in this case. You do a mole fraction, which is the moles of that chemical over the total moles. So notice I took the 0, let me switch colors here, 0, 1, 0.5, and 1. And that's what I have on top here, 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 and here. You divide them all by the total, and notice it's always the same, 2.5, and you multiply by the total pressure. This 1.26 was mentioned in the original problem, and this gives you the pressure of each chemical once the reaction's done. Of course, the CH4 is 0 because that was the limiting reactant. It's running out, so it makes sense that it's 0, and then we see what the other chemicals end up being in the answer. On a test, someone might say, well, do we really have to even mention the CH4 since it's 0? I guess it depends on how the problem's worded, but I would. Since it said all chemicals, you might as well emphasize that this is a 0, just to make sure that people know what you're talking about. And the rest of this I will talk about in class regarding the specifics of the homework. So that takes care of this lesson.